All right. Now for something a little different. In these last couple modules, we are going to work towards a new alternative way of understanding the evolution of a system. And remember, all the way back from Module 1, I even took a screenshot of this. One of our original goals of this course was to describe the evolution of a system, which we could think of as a collection of particles, waves, fields, etc., as a function of time. Or alternatively, we could say that we are trying to determine dynamical laws that, when solved, will describe the evolution of a particular system. And we have done this really up till now by solving Newton's laws of motion. Let us now try to work towards an alternative way of formulating the problem. And we are going to come up with something which is called the principle of least action, or in our context will ultimately be formulated as Hamilton's principle. This formulation of mechanics ends up being one of the most compact ways you can write the laws of classical physics. In one written line, I will be able to summarize almost everything. Mechanics, electromagnetism, general relativity, quantum mechanics, all of chemistry, even information down to the knowledge of fundamental particles. In one line, I can describe for you how all of that richness arises and where all these interesting behaviors all come from in these vastly different appearing branches of physics. So it's a very powerful statement. And given all those fields of physics I just referenced, this is something that we now know extends well beyond classical mechanics. Newton's laws of motion, fine and dandy in the classical realm, but we know of plenty of contexts where Newton's laws of motion are incorrect. The orbit of Mercury, Newton's laws don't get it exactly right. The idea, it doesn't really do that well with massless particles. Even if you kind of cheat and bring in some insights from electromagnetism and relativity, it still doesn't do tremendously well for a lot of contexts when you're dealing with, say, fields or waves or photons, things like that. Quantum mechanics, obviously when you're looking in the very, very small, Newton's laws of motion do not do a very good job, in that realm either. But this action principle that we are working towards actually works across the entire spectrum of physics. And again, it seems to be the most effective and compact way of writing down and deriving new dynamical laws. We really have not derived dynamical laws in this course, right? We've taken Newton's laws kind of as a given. And of course, lots of experimental evidence supports Newton's laws of motion in the classical context. But we never derived Newton's laws of motion. We might now, with this, we actually can work towards, given a particular principle, be able to derive something like Newton's second law. So let's set the stage and work towards that here. So again, recall the basic goal of this course was to get the trajectory for a system, or to derive dynamical laws. And usually, or at least up until now, how did we get this r as a function of t? By feeding in initial conditions, which we can write down as, say, the initial position as a function of time, and to write it the most compact way, the initial momentum as the function of time. And then we use those in solving Newton's second law, which again was that the net force on a system equals the time derivative of the momentum of the system. Given those initial conditions, I can use those to solve Newton's laws of motion. That then allowed me to get a unique trajectory for the system. And again, think of it, kind of makes sense. Newton's second law is a second order differential equation for positions. So I need, in 1D, for example, at least two pieces of information because there'll be two constants of integration when I do that. When I solve Newton's second law, so I need two pieces of information, maybe an initial position, an initial momentum, and then that can uniquely determine the trajectory. So let's start by first taking Newton's second law as a given and ask ourselves, what is the minimum amount of information I need in order to solve the system, given Newton's second law? And notice I already kind of am working towards being as compact as possible. I could have written down initial positions, initial velocities, plus the mass. And that might seem like I need three pieces of information. But really, since Newton's second law is talking about a time derivative of momentum, really I can combine the mass and the velocity, which we call momentum, and I only really need the positions and momentums to get me going. But what about in other contexts where we have or in a more general context where we have multiple dimensions and multiple particles maybe? Well, let's reason by induction. Suppose I have one dimension, so I'm going to say capital D equals 1. That's going to stand for dimension. And capital N equals 1, and that's going to constitute the number of particles. Well, in that case, then the initial conditions might just be I have to specify some sort of initial position, which let's call that axis X, and then I have to specify some initial momentum, but in 1D that's just going to be some single number, the momentum, say, in the X direction. So it looks like in this case I need two pieces of info. If you give me those two numbers, I can solve Newton's second law, and I'm off and running. What about if the particle is moving in two dimensions, but there's still only one particle? Well, then R naught might be X naught and Y naught, where the initial momentum might be P naught X, P naught Y. So it looks like in this case I need four pieces of info. 3 dimensions, one particle, 6 pieces of info. 3 for the position, 3 for the momentum. So it seems like in this case, there's a factor of 2 kind of flying around in there. Let's consider this by changing the other variable and see if we can generalize. So let's go back to 1 dimension, but there are 2 particles flying around. Well, in this case, there might be 2 initial positions. And I might call it R naught and R naught 1, the initial position for particle 0 and 1, say. And that might be written down as maybe X naught and X naught 1. Each of those vectors has one number. Then there might be 2 separate momentums, a momentum for each of these particles, which I might write down as P naught and P naught 1. In this case as well. So it seems like in this case, there are 4 pieces of info needed. When it's 1 dimension, but 2 particles. What if D equals 1, but N equals 3? Well, then there'll be 3 positions, 3 momentums. That seems like 6 pieces of info. What if D equals 2 and N equals 2? Well, then R naught might be X naught, Y naught, but then R naught 1 might be X naught 1, Y naught 1. And then the momentums are similarly going to have 2 pieces of info each. So you got 2, 4, 6, 8. Looks like you need then 8 pieces of info. So putting this all together, it looks like for the dimensionality, as D increases, it looks like I need twice the number of dimensions. And then it seems like as I increase N, I'm going from n equals 1 to 2. Right, that also is a factor of 2 from n to 3, kind of added 2. So in general, it looks like you need something like 2dn pieces of info. To fully specify the evolution. And again, it's that we needed, right, you can kind of reason yourself, that that's the case for all these things. If you can think of how many pieces of info is needed for a single particle as a function of the dimensions, and then how does that number change as you tick up the number of dimensions on that particle. I might add on to this sentence and say that pieces of info to fully specify the evolution of the system through what I'm going to call physical space. And physical space is just, space, right? If I want to determine the trajectory of a ball that I throw in this room, right, I'm going to specify its motion through this kind of 3D physical space. So we've kind of been working through that all semester. We have some intuition about what that means. We are now going to try to formulate the problem in a slightly different way. In this way that we're going to formulate the problem, we want to be equivalent to Newton's second laws, to Newton's laws of motion rather, in the classical context, right? We can't come up with an alternative way of describing the evolution and somehow get a different answer compared to what Newton's laws say in the context where they both should be correct. So we want to come up with an alternative way that will be equivalent to Newton's second law, or Newton's laws in general, but we want it to be unique enough so that we have some reason to believe it might persist beyond classical mechanics. So let's formulate that here. But first, let me give you a quick example of evolution through physical space, because we're going to use this kind of as comparison going forward. So for example, right, if I were to say there's a 1D single particle that is slowing down and stopping at the origin. This might be something you want to draw. Maybe you want to draw the position, let's call it x, as a function of time. It might be that you have some initial conditions where I could ask how much information do I need? I'm going to need an initial position, an initial momentum or initial velocity. So I might have some initial position and some initial slope here, which would constitute the velocity. And then through Newton's laws of motion, by solving that, I could then figure out the trajectory as a function of time, and it might, look something like that once you solve Newton's laws of motion. And if I were to look at, say, tangent lines at certain points, right, those tangent lines would then give me the velocity as a function of time, where each of those little blue dot locations gives me the position as a function of time. So I had some initial launching point. Newton's second law gave me the entire trajectory. Now let's formulate this in a slightly different way. I could still ask myself, how much information do I expect to need if I am going to solve for the trajectory of the system? Well, I still expect in general to be requiring, 2dn pieces of information. So I still expect to need, 2dn pieces of information. But instead of specifying initial positions and initial velocities, we're going to do this a little differently. And instead of specifying everything that's going on at the beginning, we're going to specify only positions at the very beginning and the positions at the very end. So, and let me write that down. Instead of specifying initial positions and velocities, again, we would need 2dn of them, or essentially nd positions and nd velocities. We will specify d times n positions at the start and dn positions at the end. It's the same amount of information, right? It's still 2dn pieces of information. But some of that is the information we know of how things start, or essentially where things start, and dn pieces of information at the very end. So let me go back. So let me phrase this give the example in the 1D case. Again, using the example above of the particle slowing down towards the origin. Right. So again, that if we want to draw this as x as a function of time, the information that we're specifying is that there is some position here, which I'll say x at t1, and then there's some position here, which I'll say x at t2. That, again, is the same amount of information as, say, specifying an initial position and an initial velocity. But in this case, right, we are including stuff from the starting point and at the end point. This information at the start and end defines what we call the configuration of the system. Configuration of the system. And the configuration can be thought of as what is the information I need to specify how the system is configured in, say, physical space, which could be just, the position of this one particle specifies the configuration of the system for this one particle moving in 1D. I know exactly where to find and locate that particle. For multiple particles, it could be the initial positions of all of those particles. That would tell me the configuration of the system. Take a galaxy, right? If I specify the 3D positions of all the stars in the galaxy, that would then specify that all the information together would specify the configuration of the galaxy at one point in time. Not worrying about the evolutions, but the configuration of a snapshot in time. Then I could do that again at the end, at some later time, right? The configuration of the system at some later point in time, where I could specify the location of, say, the one particle or the two particles or all the stars in the galaxy. And then for these two different arrangements, I could ask, how are they connected in time? How do I start with this and end up with this sort of configuration? So it sounds very similar, but it's really specifying the problem in a very, very different way. So we are rephrasing as such. I'm going to introduce some new words as well, in that you specify the configuration of the system using, in this case, I guess d times n, here's a new phrase, generalized coordinates. i.e. coordinates that tell me how to uniquely describe the system. So say so coordinates to uniquely find the configuration of the system. And you do this both at the start and the end. So it's not a period. So they are separated probably by 2 points in time. So you have some initial configuration state and some end configuration state. And the dynamics problem, again, the task of finding the evolution, is to ask how it got from one configuration to another. Say how it got from one config to another. So this is an evolution through configuration space. If we go back up to our example here, right, our example here had, that you started at some initial with some initial configuration, which for one particle is just you have some initial position, and at some time later it's located here. And you could ask, how did the system get from here to here? And particularly, we know that, again, if it should be identical to Newton's laws of motion, that it should look something like this, like what I drew above. Right, that there was some path it took to go from one particular configuration, which in this case was just a position of that particle, to some final configuration, which was a different position for that particle at some later point in time. Now again, why this is different, besides just that we're using not just initial conditions, but we've become initial conditions and ending conditions of just positions, or generalized coordinates, that specify some sort of configuration positions, is that again, it's a different problem because before we had some starting point and we had, positions and velocities that allowed us to kind of follow the tangent lines, which the tangent lines were then given by Newton's laws of motion. Here we know how we start and how we end, and we're asking ourselves how you can evolve through those positions. Because I know that there is an infinite number of ways I could connect these two dots. Right? I drew one possible way in blue, but it could have did something like that, or it could have done that, or it could have went over here and then did that, or kind of looped around here and then did that, or maybe it just exactly followed the blue, but there was a little hiccup, at one little point. All those black curves are just a few examples of other ways it could have started at that point at the left and ended at the point at the right. But again, in nature, only one particular path is followed. So there is something happening where nature says, we're going to take that blue path between the 2 points, not any of those curves I drew in black. Something is determining that. or there is some rule that nature seems to be obeying in order to say it's the blue path and not any of the other ones. What's special about that blue path that's different from the other ones? That's what we're trying to get towards, and hope that if we can give that answer, then that suggests we might be able to figure out a way of how we can calculate that special property that the blue curve has, which maybe allow us to kind of pluck out the blue curve from the infinite other possibilities of how you get from one point to the next. That might seem daunting, right? If there's infinite possibilities and I have to find one, the one that satisfies something. But you've already done things like that, where there could be infinite possibilities and you have found ways to pick out one particular case. Let's just take two, if I were to ask you the question of what is the shortest distance between 2 points, you would say a straight line. But there's an infinite number of ways I could draw a curve without lifting my pen between 2 points. And I could draw a bunch of them and take a little ruler and measure the length of all of those things. And there would indeed only be one that has a well-defined extremum, in this case a minimum, distance, which would be the case where it's a straight line between the 2 points. You could do the same thing on the surface of the Earth. In that case, the surface is curved, so you can't draw straight lines. But again, you could figure out there is one particular path that minimizes the distance between the 2 points. It's called a great circle, a circle that is, I guess, co-centered at the center of the Earth with the radius of the Earth, which is why when you see like the paths that planes take from one point to the next on a flat screen, if you're like looking at the screen of the map on the back of an airplane seat, right? It looks like the plane might be taking some weird arc curve. Really what it's doing, it's taking the shortest distance between the 2 points, but on a curved surface like the surface of the Earth, that shortest distance actually is, well, it can't be a straight line, but it's some sort of extremum curve that's being calculated. All right, so our goal here is that we need to try to figure out a way of, one, what makes that blue curve special? And two, is there a way that we can prescribe a way to write down or calculate that special property for a particular curve so we can find that blue curve? But for the rest of today, let's delve into a couple simpler examples that helps us get a little bit more of a feel for what I mean when I talk about configurations and generalized coordinates. For one particle, it seems like physical space and configuration space are the same, and they more or less are. For 3D or 2D, right, I could write down the position in physical space by specifying, say, a 2D or a 3D vector. That tells me kind of where that particle is at one moment in time. And that also kind of defines itself in configuration space at one moment in time. This becomes a little bit more abstract and interesting when we extend this idea to systems. Because again, most systems in nature are not a single particle. So then, for example, what if you have 2 particles moving in 1D? Now again, with the idea of configuration space is that we said that we need 2 ND pieces of information total. But that included ND pieces of information at the start and ND pieces of information at the end. Assuming nothing like that the particles are coupled to one another or something like that. We'll get to that in an example in a little bit. So for 2 particles in 1D, I might expect that I need 2 pieces of information, 2 times 1 at the beginning, and 2 times 1, 2 pieces of information at the end. And it makes sense what those 2 pieces of information would be. So let me draw this in physical space. So if this is 1D, right, maybe I have an origin here, and there's some axis. And maybe at some point the first particle is located here, and then the second particle initially is located here. And then at some point later in time, so there's some delta t that occurs. At some point later in time, maybe later in time we find that the blue curve has moved all the way out here and that the red curve has moved out here, say, after some later point in time. So it seems like the particles have moved. How could I describe this motion in configuration space? Well, configuration space is going to be two axes again, but the axes are going to be the position or configuration of particle 1 and the configuration or position of particle 2 in this case on the axes. So in the case of the initial positions, it looks like x1 is pretty far out from the origin, so maybe here. But then x2 is also to the right of the origin, but not as far out as x1, so it might be only located, say, here. So if I were to trace those out to where they intersect, this point here, x1 comma x2, which is the two positions of the two particles, that is the configuration of the system. That single vector encapsulates the entire configuration of the system, how the entire system is arranged at one point in time, which has about, if x2 is 1 inch away from the origin, it looks like x1 may be something like 2 inches away from the origin. But I could specify that all as a single vector that tells me the position of particle 1 comma position of particle 2. Later on, at some later point in time, it looks like x1 gets closer to the origin, so it might be located, say, here at some later point in time. And it looks like x2 starts to move pretty far from the origin, so it might be located up here at some later point in time. So again, if we trace out their locations in this 2D space, this point right here, which might be x1 prime, x2 prime, say. And I'll mark that over here. This might be x1 prime. This might be x2 prime. That second black dot is the configuration of the system at some different point in time, t plus delta t forward in time. So again, this is not x as a function of time, because both axes are positions, and they are positions for different particles. But that one dot on the graph tells you the configuration of the entire system, in this case, two particles moving in 1D. And then, again, the dynamics question is, what is the path that it takes? Right? There's some particular path that as long as I know the force is acting on the object, or maybe we'll come up with a different thing we can think about in terms of how systems evolve. There's some particular path that the system takes to get from one configuration to the next, compared to the infinite ways you could get from one point to the other. There's something special about that path. We don't quite know what it's going to be yet, or how to figure it out, but that is, again, what we're aiming for. This configuration space is abstract, because again, it's not physical space when there are multiple particles. So what if you had, say, 3 particles in 1D? Well, then to specify the configuration at some starting point in time, I expect 3 times 1, or 3 pieces of information are needed. At the end point in time, I need 3 times 1, or 3 pieces of information to specify the situation there. Right, so again, if I had some 1D axis, right, it might be that I have some x1, maybe this is x3, then maybe this is x2 at some point in time. And plotting this in configuration space, would be, I have some axis that tells me what's going on with x1, one axis with x2, one axis with x3. Looks like x1 is kind of at a medium distance from the origin. X2 is pretty dang close to the origin. And then X3 is a decent way from the origin. So maybe it's kind of up here. So then if I trace this path up from the shadow, looks like I might say that this location here, this one dot, which is x1, x2, x3, specifies the configuration of the entire system. That one dot tells me everything about the system. If this were a galaxy with 100 billion stars, and I had a way of writing down a plot that had 100 billion axes, I could put one dot on that 100 billion axes plot, and that one dot could then be used to specify the configuration of that galaxy. You know, the location of, I guess in that case, I'm assuming it's 1D, right? Which sounds kind of weird for a galaxy. So let me take a step back, right? If this were a 3D galaxy with 100 billion stars, I would need 300 billion axes, and that would allow me to specify, with using one dot on that plot, I could then specify the configuration of the entire galaxy. There would be an axis for the X, Y, Z of every star, say, in that galaxy. Each one of them would get their own axis, and then that kind of 300 billion D space would allow me to specify, using a single point, the configuration of that system. You can see why I'm sticking with 1D. It becomes very hard to start drawing these things once you get to multiple dimensions and multiple particles as well. So that's kind of the idea of the basic idea of configuration space. But I've mentioned this thing called generalized coordinates, and I keep alluding to that you have to be careful that there's no constraints in the problem as well. So let me show an example of both of those, which again will be continuing to motivate these bigger ideas, and I think will be good for this module. So what do I mean by generalized coordinates? Well, your coordinate choices have options. You still need to specify, n times d values in order for you to uniquely determine the configuration of the system. And in the kind of examples above, we've always been using positions as a way to specify the configuration. But it doesn't necessarily have to be positions. Right, so you always need ND values to specify the configuration. But the form that they take might be, is also up to you. So let me give two simple examples. One will seem very obvious because we've been doing this a lot. If I have some axis, one particle in 2D. One particle in 2D, if I want to specify the dimensionality of configuration space, let me start using that phrase. The dimensionality of the configuration space. How many dimensions of or how many pieces of information are needed for me to specify the configuration? Again, I know that should be n times d. 2 dimensions, 1 particle, I expect to need 2 pieces of information to specify the configuration of 1 particle moving in 2D. And of course, if I have a particular axis, I can specify, of course, that by, say, x comma y, for these 2 axes. That then specifies the configuration of this 1 particle moving in 2D. But, of course, I could move my coordinate system, or someone else could have a different idea of the coordinate system that they want to use. Maybe they have some other axis that has a different origin, and then they draw their position vector, and it has some coordinate, x dash or x prime, y prime. Right, this might be alternative coordinates, which should be equally, important or equally applicable, if we want to use these instead to justify the configuration of the system. And then as things move from one configuration to the next, you might be able to ask from the blues coordinate system, how does this trajectory look? And of course, we want to make sure that the black axis and the blue axis should agree on some things. So they probably should be able to trace out the same trajectory if you then shift from one to the other using, say, relative motion transformations. If you can't, then that might mean that something else is in play. And we've seen that a little bit too, of just if you have a non-inertial frame, you have to make some corrections in order to make that work. But again, that's kind of a coordinate transformation that allows you to do that. So again, using different coordinate systems should allow us to still get the same answer, as long as we're careful about what we're doing. But in this case, both cases, right, the black coordinates and the blue coordinates, the configuration was defined by two positions, right, an x and a y. A third person might come along and say, I'm not going to use x and y's at all, but I'm going to use polar coordinates. I'm going to specify the position by an r and a theta. In that case, if I give you two numbers, I give you an r and I give you a theta, those coordinates, I'm kind of writing it as a vector. Maybe I shouldn't write it as a vector. It's not technically a vector, of course. But these two coordinates, r comma theta, also uniquely determine the location of that particle. So I would say these are equally valid ways of describing the configuration of the system. But notice I still needed two. I couldn't get away with only one. I still needed two pieces of information, but in this case, one was a position, the distance away from the origin, and one was an angle, the angle I've rotated from some axis that defines theta equals 0. So these are also two good coordinates, but with mixed units. Or they both don't necessarily have to have units of position, and that's okay. But again, you still needed two in this particular system, which again was one particle in 2D, 2 times 1 is 2. The configuration dimensionality is 2. Are there cases where maybe it's not the number of dimensions times the number of particles that would uniquely define the configuration of the system? There are cases like this. And that's when there are constraints, typically geometric constraints, to consider. So let's look at the example of a box on an incline. And I'm going to put my origin at the base of the ramp. In this case, if you wanted to specify, if you know the box is going to move down the ramp, it seems like for this particular coordinate system, it's moving both left and right and up and down. That sounds like it's two-dimensional. And again, you could specify the location of the box, of course, by specifying some x value and then specifying some y value. And that would give you the location of the box. So you might say that the location of box is given by x comma y. And you might be tempted to say that the configuration space is two-dimensional. But in that case, that would be incorrect. because the x and the y coordinates in this case are not independent of one another. You cannot arbitrarily change x without changing y in a very specific way. Namely, if the box is moving on the ramp, it is not possible for the x and y values to be arbitrary relative to one another. So particularly in this case, you also have a geometric constraint. Namely, in this case, if you look, there's a triangle there. Tangent of the theta, the angle of the ramp, is then going to be y over x of the box, or that the y value of the box is whatever x is times tangent of theta. So if I know x, I then also know y for a given ramp. So if I wanted to specify the coordinates of the system, I wouldn't write x comma y, but really I would write x comma x tan of theta, where again theta is assumed a constant in this case. So really the configuration to uniquely define in this case, the position of this one box, which is also the configuration of the system, I don't need two pieces of information, I need one piece of information. So the configuration requires one piece of info. So I might say the general coordinate q I might choose to be x. This is notation in your book and we will use, right? So this is, the q's are going to be used as our general coordinates. The coordinates that we're going to use to describe the system. So if I go back up here, this r theta I might have called q1 and q2 as my two coordinates. Up here back over to the Cartesian box, this might be q1 and q2 to describe the location of a particle in 2D Cartesian coordinates. In this case, there's really only, for the box on a ramp, there's one general coordinate that we can use, x. You might say, why not y? And I say, why not? But in that case, then x comma y, if I were to uniquely describe the system, I could write the entire configuration of the system in terms of y. In that case, it wouldn't be x comma x tan of theta. It might be y over tan of theta comma y. That also then would, is that right? Yes. This would also tell me the unique configuration of the system in terms of one general coordinate y. So that is the same using my general coordinate of y instead. You might say, since I'm moving on a ramp, why not polar coordinates? But then I don't have to give an arbitrary theta value. I just have to specify some sort of r value as my distance from the origin. Again, why not? Sounds great. In that case, the positions of x comma y might then transform to be something like, I guess it would be r cosine theta, r sine theta. But again, I can uniquely define the configuration of the system by just a single number. So that's using q1 equals r. And again, I could come up with an infinite number of ways I could do this, right? I could choose, what if I want to do it, again, from this place? Maybe my origin's out here, right? And there's lots of other ways I can define the unique location in a coordinate system. But again, they all should only require a single variable, x, y, r, whatever you choose it to be. So in this case, while there was 2 dimensions and 1 particle, so 2 times 1 is 2, there was one constraint which changed the 2 into a 1. So it seems like the constraints seem to take away from the dimensionality of the configuration space. In this case, there was one constraint, and I ended up subtracting 1 away from n times d, which was 2. Let's see if that holds for other examples. Let's take the pendulum. Let me put my origin here. So it's swinging, there's some angle theta, it's a length L, usual stuff. Again, if it's swinging back and forth, you might think, that seems like a two-dimensional problem because there's one particle, the pendulum, or the bob of the pendulum, and it is moving in 2 dimensions, right? Its x value and its y values are changing. So it seems like you need 2 pieces of info. But, again, there is a constraint. It can't be arbitrarily anywhere, but there is, so there's, one particle, 2 dimensions, but there is a constraint that, and I put my origin there, so it would be easy to write down. So this particular constraint says that x squared plus y squared better equal L squared by the Pythagorean theorem. There is a relationship between x and y. I cannot have x and y be arbitrary. So again, if you tell me x, I can then tell you also y. Or if you tell me y, I can also tell you x. So it seems like the configuration of the pendulum is a one-dimensional configuration. So I could use, for example, q1 equals x, or q1 equals y to describe the entire problem. Or, since I, again, am not constrained to only use positions, why not theta as my generalized coordinate? That if I give you a value of theta, I could uniquely draw what the pendulum looks like at that particular theta value. Because I know how long the pendulum length is, and I know where where it's kind of originating from, where I put my origin. I could uniquely draw the pendulum for a single value of theta. That then uniquely defines my configuration. But again, I had one particle, 2 dimensions, so I expected 2 pieces of data, but I had one constraint that turned the 2 into a 1. This is a one-dimensional problem in configuration space. One more, and then I think you'll be able to generalize. Let's go back to that ramp. There's a box on a ramp, but then it's attached to a rope which swings around a pulley, and there's another box that's hanging down vertically. And those 2 boxes might move, if the box on the ramp moves up and down, the box that's hanging also might move up and down. Maybe my origin is somewhere like here. So now that seems like there's motion left and right, and there's motion up and down, so it seems like the number of dimensions is 2. Now the number of particles is 2, right? Because I have the motion of box 1. Maybe we'll leave a box 1 and box 2. So this might suggest that I need 4 pieces of information. But again, there are constraints to consider. What is the minimum amount of information that you would need in order to draw a picture that would uniquely show me what the system looks like? Right? Naively, this suggests that I might need 4 pieces of information. But then there is 2 constraints in this case. There's again the constraint of the ramp, so I know that y1 over x1 must be tangent of theta. So there is a relationship between those 2 coordinates, so that reduces the dimensionality by 1, so it goes from 4 to 3. But then there's also the rope constraint. In that if the rope is a fixed length, the 2 boxes cannot be arbitrarily located away from one another. There is only a set number of locations. If one box is on the ramp and one box is hanging, and the rope that is connecting them is a certain length, there is a relationship between the position of box 1 and the position of box 2. That further reduces the dimensionality again. Because you imagine it's going to be one kind of equation that involves x1, y1, x2, y2. we already know there's a relation between x1 and y1. And then the rope constraint then gives you another relationship between, say, x1, x2, and y2. So you have two equations with three unknowns. Of course, it's not something that you can solve for x1, all of the coordinates. And that would not make sense if you could, because then there's no dynamics going on there. But that does give you at least a relationship, like you could solve for x1 in terms of x2 and y2, and then you could get then ultimately about a bunch of equations that only depended on x2 and y2. So then in this case, this reduces the dimensionality of configuration space by 1, and this reduces the dimensionality of configuration space by 1. So it's not a 4-dimensional problem. It's actually a 2-dimensional problem. I only need just to give me two of these numbers, x1, y1, x2, or y2. Give me two of those, and I can uniquely tell you where both boxes are. Because the two constraints, the geometric constraint of the ramp and the geometric constraint of the rope, then make all four of these coordinates not independent of one another. So in general, the configuration space of a system in d dimensions with n particles and c constraints For the ramp alone, there was one constraint. For the pendulum, there was one constraint. For the ramp plus rope, there were two constraints. So in general, I guess the configuration space of a system in d dimensions with n particles and c constraints has dimensionality. I guess what will I call this? Maybe DIM. The dimensionality of configuration space will be d times n minus the number of constraints. And that deserves a highlight. And that what is the minimum amount of information I need to uniquely determine the dimensionality of the configuration? Well, it's the number of physical dimensions times the number of particles, or number of objects in the system, minus the number of constraints that exist between all of those objects. That then gives me the minimum amount of information to determine what the system looks like at a moment in time. And again, that then is the minimum amount of information I can use to specify the configuration of a system at some other moment of time. And then, a piece we're still missing is some sort of rule that allows me to connect one to the other. And we will continue working towards that.